Alright guys, now we are here at stereoisomerism. Now, under stereoisomerism, we have two other isomerism under stereoisomerism. We have geometric and optical. First, let's take geometric. Now, geometric isomerism. How do we now differentiate between this and the rest we have been doing? It's simple. See how we do it. Alright, now let's use a compound. Which compound should we use? Now let's go with this. We go with, first of all, okay, alright. Now, take a look at this compound. I think this is the simplest compound I can use to explain this. Alright, we can also use compound exchanging these substituents to something like what they call it, halogens like chlorine, bromine, iodine and all that. So we can also do that, but let's go with this. Okay, now looking at this compound, is this compound different from this? Actually they are the same, but they look like they are different. Now if you want to name this, how do you name this compound? Okay, if we say we can count from anywhere now because it's the same substituent, substituent, so we can count from anywhere. Now let's count from 1 2. So now if we want to name this, we'll name it 1 2, because there are 2 methyls here, we'll name it 1 2 dimethyl ethane. 1 2 dimethyl ethane. 1 2 dimethyl ethane. Okay. Now, fun fact, if we want to name this, how do we name it? Still the same thing, the same substituent, so we just count from anywhere. 1 2. So if we want to name it now, we also name it 1 2 dimethyl ethane. So these two compounds are the same. Now, how does this relate to what we are saying? Since these two compounds are the same, why are they the same? Because there is a free rotation of the substituent. Because of the single bond here, this substituent can rotate, can change their position. So there is no how you recount it that they will always appear the same. You get? But now, if we decide to change this thing to double bond, what will happen? There will be a resistance to the what they call it, to the rotation. So now let's change this thing to double bond. Alright? If we change it to double bond, what will happen? Okay, we now have something like this. Okay guys, let's change this one also to double bond. We now have something like this. Okay, now from the look of things, you will think they are the same, but they are definitely not the same. Due to the presence of this double bond, these substituents can no longer change their position, which means they will remain like this even when we are naming it. Like this one now can't change to this side, so definitely this guy is a different compound entirely. This one is a different compound entirely. What you have to note about this is that since they are different, they actually have different physical properties because their structure is actually different. Okay, under stereoisomerism. Okay, so now what do we have to know about isomerism? I will just give you 5 points in which it will be very clear and easy for us to know how to differentiate optical isomerism from the rest isomerism. Okay, now first, For an organic compound to be able to perform optical isomerism, it must first rotate a plane polarized light a certain degree. Alright? Now, first of all, if you must rotate a plane polarized light a certain degree, that's the first one. Note it. Secondly, it must vibrate at one place, inclined 90 degrees. This is the second point we should note. Now, thirdly, it must be asymmetrical. It must be asymmetrical. Alright, this is the third one. Fourth, it must what? It must have a chiral center. It must have a chiral center. Are we good? Then finally, the most important, it must have four different substituents. Must have four different substituents. Alright, it must have four different substituents. Okay, now these 5 characteristics of a optical organic compound which can exhibit optical isomerism. For any organic compound to be optically active, it must perform these 5 things here, these 5 characteristics here. If it has performed it, which means it's optically active. After performing these 5 characteristics, we cannot say this compound is optically active. And if they are optically active, they can actually create a mirror image of themselves. You know how you stand in front of a mirror, you notice that if you raise your hand here, the mirror will raise its other hand in this other side. We can call that laterally inversion. You understand? So these organic compounds can actually create a mirror image of themselves which are laterally inverted. It is then said that these organic compounds are optically active. So take note of these 5 characteristics. Okay, now finally, every compound which are optically active, which can create a mirror image of themselves, are called enantiomers. Alright, now let me write it. They are called enantiomers. Don't forget, they are called enantiomers. Now let's move over to the examples of organic compounds which can perform optical isomerism. Alright, now the examples of optically active organic compounds. All amino acids are optically active except for glycine. Glycine is the only the non-optical organic amino acid. Glycine is the only amino acid which is not optically active, but the rest amino acids are optically active. Note that. So now let's draw the structure. Okay, this is an amino acid. Now, from the look of things, if you remember all the characteristics listed, you will notice that this thing possesses all the characteristics. Like the way we said, it possesses 4 different substituents. Exactly what is it? So note that is a very important point. Now, as we said, it will create what? It will create a mirror image of itself. How does this compound create a mirror image of itself? Now, it's like this. The mirror image of itself will appear like this. The the carbon will not move because it's actually at the center. So exactly, this is how it will appear. The mirror image of this compound will appear like this. Now, this compound is now called amino acid. This is dextrorotatory, and this guy here is levorotatory. Now, why is it called dextrorotatory and why is it called levorotatory? Now, this guy rotates to the right side. Every organic compound that is optically active that rotates its polarized right is polarized right. Any organic compound that rotates its plane polarized right to the right hand side is called dextrorotatory, and the one that rotates to the left hand side is called levorotatory. Are we alright? So now it's just simple, this dextro and this levorotatory amino acid. Alright, this is how it looks like. Now let's clean the board and draw another example so that you can see. I think we are going to draw lactic acid now. This is amino acid. Let's draw lactic acid. Alright, lactic acid is the structure of lactic acid is like this. Okay. Yes. Alright. This is the structure of what? Lactic acid. Alright. Now, since it has the characteristics of an optically active organic compound. Let's draw its opposite side, a lateral image of itself. Alright, so now this is how we draw it. So we have to write this guy like this. Okay. Note these examples I'm giving you. Lactic acid is one of the examples of optically active organic compound. Lactic acid and amino acid. Now, how do we now know which of them is actually dextrorotatory and levorotatory? Now, this guy is facing the right hand side, so it's called dextrorotatory. Note it. Dextrorotatory lactic acid. This guy is called levorotatory lactic acid. Alright. Now, these guys. Alright. Now, we all know what enantiomers is. But now, there's a foreigner in our midst. That's stereoisomer. What is the isomer? Okay. It's more like this guy. It has every other thing than this guy. But unlike this guy, the stereoisomer has two chiral center. It has two chiral center. Alright. Now, for us to be able to understand what a distereoisomer is, let's take an example, which is tartaric acid. Tartaric acid. Now, that's the example we're going to be using. So now let's draw tartaric acid. The structure of tartaric acid is this. Alright. Okay. Sorry. I forgot we're drawing a distereoisomer. I'm sorry. It's drawn like this. Okay. Yeah. And our wish. Okay. And finally, okay, this is how tartaric acid look like. Now, since there is stereoisomers, most times due to their double chiral center prevent them from having a exactly mirror image of themselves. But tartaric acid is special. Tartaric acid can actually perform anatomy. It can also be classified as an enantiomer. It can have an enantiomer and also a diastereoisomer. So do you get what I'm trying to say? I'm trying to say that this compound here called tartaric acid can produce what? A mirror image of itself. Okay, this is how the mirror image of itself is drawn. Okay. Alright. Okay, follow me. You get. So now, due to this double chiral center, the rotation can be limited. So it can actually rotate and produce an enantiomer, which is exactly opposite or laterally inverted image of itself. But also it can also, there's a way it will try to polarize the light. It will be able to produce exactly the same opposite image of itself, which is why it can classify under enantiomers and diastereoisomers. Okay, do we understand? Okay guys, this is all we need to know about isomerism. I tried my best to be able to cover it, and we've actually covered it. So anything about isomerism, I trust you can deal with it in no time. It is okay. So thank you for watching.
I see you have about 23 boyfriends in your life.
Yes, sir.
Huh?
Yes, sir.
23 boyfriends.
It not that easy, oh. It not that easy, oh. 23 boyfriend, only one girl.